Hello, in the previous video, I showed you how to prepare train and test data for our Lasso and ridge regressions. When I say regressions, you would be dreaming about coming up with a value, with a numerical value on the predicted or dependent variable. In this case, our ridge and lasso regressions are going to be used for classification purposes. So the outcome is going to be very similar to the outcome that we implemented in logistics regression. So we will be predicting whether the lasagna, our customers coming into our stand, whether they are going to be trying our lasagna or they're not trying our lasagna, okay? So we are going to be using Lasso and ridge regressions classification aspects. So just to get it clear on the video, okay? So in the previous video, I showed you that we have to implement one hot encoding on both train and test data. And I keep all the independent variables for my train data and test data separately with the additional dummy columns. So they are stored under train X and test X data frames here. One thing that I want you to pay attention to is the fact that neither train X data nor test X data contains my dependent variable. I'm going to be calling my dependent variable directly from the train and test data frame, okay? That's one of the requirements that comes with the glmnet package. All right, so at this point, if you have not installed this package called glmnet, I would like you to uncomment line 34 and execute this line to install glmnet package, okay? Pause this video after you install it. Make sure that you uncomment this line and come over here and execute library glmnet comment. By this way, you would be loading glmnet package into your um, R directory, and then it is ready to be used. All right. So let's get first started with the lasso regression model. You will see that there's going to be only one parameter that's going to be different between the lasso regression model and also the ridge regression model, and that's going to be the value of alpha. All right. Before I go further deep down, let's call the help menu of the glmnet, and let's take a quick look into it to see what it looks like. So it basically tells you the description of this data set, and then the glmnet of formula or the function, it tells you that you should first put the x values, meaning that independent variables, and then the dependent variables separately, and pick up your family. In this case, we are going to be picking up binomial family because we do have two outcomes in our dependent variable. For example, if we had 3 or more, we would be picking multinomial from the family, okay? And then those are certain weights. This alpha parameter is going to be very important. If alpha equals to 1, we would be implementing Lasso regression. And if alpha is equal to 0, then we would be actually implementing the ridge regression. As a matter of fact, that's what we're going to be changing later on to implement the ridge regression. Okay, that's only that thing that we are going to be changing. So with Lasso and Ridge, regressions, there is a shrinkage variable or the penalty factor that we have to consider. All right. So at this point, I should be talking about two great articles that I'm sharing with you. The first one is a guide to ridge, lasso, and elastic net regressions and applying it in R. So I also I shared the link of this article with you, and I attached this as a PDF on Canvas. Make sure to take a good look into it. As I said, you do not really need to worry about the certain aspects of this article, but make sure that you understand what Lasso and Ridge is providing us. Um, One thing that I would like to highlight is the fact that we do in our traditional multiple linear regression model, we do try to minimize this function, okay? This function is basically taking a look into the differences between the actual values and the fitted values, and we would like to minimize this error. Okay. In actually in Lasso and Ridge, we further go and add a certain parameter into the equation. So what we do is, in addition to this function that I just showed you, which is basically measuring the squared deviation from the fitted values, what it is doing is it is adding a certain penalty factor into the equation. Um, and, um, and the way that it does it, it's called L2 regularization. This is the mathematical explanation to it. You don't really need to know certain details on it, but I just want to highlight the fact that these are the coefficients, and this is the L2 term, this is the L2 norm. This side, the sum of the L2 norms to this side, multiplied by a parameter called lambda. This is called shrinkage factor or penalty factor in Lasso regression and ridge regression. I'm sorry, this was the ridge regression that I was showing you. It wasn't Lasso. Let's make sure that we are talking about ridge regression. Yes, we are actually talking about ridge regression. And other name that we use for ridge regression is actually L2 regularization. All right. So we do have the same lambda parameter for Lasso regression, but this time we are using L1 norm in the equation, adding it to the traditional residual sum of the multiple linear regression equation. The reason that I'm showing these to you is the fact that in Lasso and ridge regressions, one thing is common, and that is actually fixing this lambda variable. Okay, we try lots of different lambda values so that we could optimize this deviation into the equation. And one great features of Lasso and ridge regression is the fact that they are going to be trying to remove multicollinearity out of our regression model. All right. But how do they do that? Well, they look into certain coefficients and they try to set the ones equal to zero, the ones that are sharing information between each other, right? That's actually the explanation of multicollinearity, right? Your independent variables, they do explain each other, and then they create a lot of noise in your data, right? And they might inflate the p-values, inflate the t-statistics in your statistical model. And Lasso and ridge regression has a great shape and feature with this lambda penalty factor. And the reason that we call this shrinkage factor or shrinkage value or shrinkage term is because they are trying to attempt to move these coefficients of certain independent variables to zero or close to zero in ridge regression's case, so that we will be dealing with a very few number of independent variables. Lasso and ridge regressions are very useful when you have, let's say, hundreds of thousands of independent variables, and some of them are basically, very similar to each other, right? If you have that kind of problem or um, curse of the dimensionality in your problem, the way that you can handle it, Lasso and Ridge might just help you out with that, right? So they might be used to further reduce your dimension into a smaller scale or smaller number of independent variables, so that your model would be very simple, and it would be reliable, hopefully. And that depends on the training. Well, speaking of training, in this video, we are going to also take a look at cross-validation, k-fold cross-validation more specifically. You remember that we split our dataset into train and test. While on further training dataset, we do create several folds. So in this example, and in my example in our script file, I'm going to create randomly 5 folds on the training data. This is going to split the data into 5 different sections. and then it's going to take the first fold again for using it as testing purposes and using the last four is as the training data. And it's going to do it 5 times and selecting each fold as testing and the remaining other 4 folds as the training data to increase, hopefully, well, actually to decrease the overfitting and to further improve the parameters and the characteristics of your training data set. We further train our data and then we further test it on our test data. Okay, and that's going to be changed with the test data, but we do the k-fold cross-validation on the training set like this. So this article is also shared with you. Make sure that you take a good look into it, and it explains the main motivation between k-fold cross-validation. In R, the implementation of these things are very, very simple. You won't even realize that we are actually doing cross-validation and k-fold cross-validation. GLMnet actually is the function to fit a certain lasso and ridge model. While on the other hand, cv.glmnet is the function that is going to enable us to use k-fold cross-validation on top of lasso and ridge regression. All right. So how does it work? Well, it's going to be similar to the glmnet function. Let me see if I can find the cv.glmnet here. I don't think I will find it here. The easiest way to get it on the help menu is to copy and paste it here. Yes, now it will bring it up. The usage is going to be very similar. In the cv.glmnet, it's going to return a lasso model for me when I specify alpha value equals to 1. As I said, if you change alpha value to 0, it will be a ridge regression. And then I'm going to show you how I do it over there at the very end of this video. And I would like to, let's say, split my training data further into 5 folds, and I want each fold to be selected as testing purposes in my training set. And after you read that article, it's going to become clear to you. And I'm going to specify my alpha value as 1. My family is binomial because I'm dealing with 0 and 1s, just 2 outcomes. Type measure is class because this is actually telling the cv.glmnet that, hey, go ahead and implement lasso on this problem in such a way that your prediction is going to be on the final dependent variable, like 0 and 1s. Okay, type measure class is going to help us predict 0s and 1s, not probabilities, not something else. Okay. And then the first spot is going to be the spot for the train X data. Remember, train X data frame here does not include my dependent variable. Only one hot encoded independent variables is included in the train X. And then similarly, only independent variables, one hot encoded independent variables are included in the test X data. Test X data does not include the dependent variable. I'm going to be using my dependent variable, directly calling it for this time from the training data set, right? I directly call the have tried column directly from the training data frame. Okay, the reason I do it is because cv.glmnet, the first spot belongs to independent variables, all independent variables. It should not include dependent variable, okay? All right, so this is ready. Let's execute this. Again, CV Lasso is just the name that I gave. You could change it to anything that you want. The model comes with lots of different features. With a $sign, you can call them. Basically, it went ahead and fit or tried 69 different Lambda values, these Lambda values that I showed you. I was talking about these Lambda values here. It tried 69 different Lambda values, and hopefully we can actually retrieve the best of them. All right, so let's first plot it, see what it looks like. Well, in this plot, you will see the benefit of cross-validation, okay? On the y-axis, it's actually telling us the misclassification error of these classes. On top, you see the number of independent variables this Lasso regression is using. And right here on the first dash, vertical dash line, actually our model is selecting the lambda value. This is the log lambda scale here on the x-axis. It will be the minimum log lambda value that gives me the minimum mean classification error when the model works on the k-fold cross-validation. So it is actually giving me the optimal lambda here. It also gives me another lambda value, and this is called 1 SE lambda, one standard deviation further down, by compromising a little bit on the misclassification error here, okay, I am further simplifying my model down to 4 independent variables. I'm going to show you which coefficient values are going to be active here and here, but it is important for us to know how to interpret these ridge and lambda plots. So this is basically what it means. So the optimal lambda value is going to tell us to work with 5 independent variables. And if you sacrifice a little bit misclassification error here, you would be working on a much simpler model. Sometimes you're saving 1 independent variable here from here to here. Sometimes you would save, if you have like hundreds and thousands of independent variables, sometimes you would, by a simple a little bit comprising a little bit on the misclassification there, you might save a lot of independent variables. You never know. In this case, we just saved 1. All right. Let's go further. Let's try to see our lambda values that the model tried. All these lambda values were tried. And let's see, this is the minimum. This is the optimal lambda value. Actually, let's put it before the 1 SE, 1 standard deviation. So this would be the lambda value with 1 standard deviation here. And this would be giving me the lambda value, the optimal lambda value. Let's call it, it will be 0.003391326. And as I said, this lambda value would be a little bit higher than, well, actually a little bit higher than my optimal value, but it's going to actually enable me to get rid of 1 independent variable. All right, let's take a look at the coefficients of these independent variables when the lambda value is at its minimum and when the lambda value is at 1 standard deviation above the optimal value. All right, so let's take a look at the coefficients. You remember that these are all my independent variables, and whenever you see a non-zero variable, it means that it is actually active here, right? So these are the coefficients when the lambda at its minimum level. If you pay closer look into it, you'll see that at lambda at min, I'm using 5 independent variables. So let's see which of these 5 independent variables that I'm using. Pay tab celerity is something that I will be using. Leave alone yes is going to be something that I will be using. Neighborhood vest is something that I will be using. And H value I will be using. And mole trips I will be using. So different than the logistics regression, I don't see any other, well, neighborhood saw variable here, right? I don't need to use it compared to logistic regression. That's one thing that I can get rid of based on Lasso. Let's take a look at the 4 independent variables as suggested by this plot of this Lasso. Right? Let's see which of those 4 it is suggesting me to use. It is suggesting me to use, again, pay tab salaried, neighborhood vest, age, and mole trips. So it cut off which one? Let's see. Age, neighborhood vest. Okay. It cut off this little on variable, yes variable. It's no longer active in this, of course, in this lambda value level. So depending on your selection, so if you would like to really work with very few independent variables, you can go with this lambda value. If you think you are losing too much and it's a crucial value, important independent variable for your problem, you could go with the optimal lambda value. It's up to you, simply. Okay, So we trained our model like this with just one line of comment, right? We trained it. Now we can make predictions with it. All right. This is how you can retrieve these coefficients, and then you can take a look at what it is giving to you. But let's take a look at how we can actually make predictions. Well, we are going to be using predict functions, and then we are going to keep those predicted values here. Of course, we are going to make the predictions first on the trained data to see how much our trained model, um, the accuracy of our trained model is. Of course, we have to specify type as class because these predictions are going to be in terms of zeros and ones, no longer probabilities or in other measures. Then you put it in class mode. The new x, this is the new x or independent variable set. I'm still going to be using my training data because I haven't looked into the confusion matrix on that. And this S value is going to be asking you what lambda value you would like to use. So I prefer to go with the lambda value that gives me fewer independent variables. You could have selected easily this lambda min, but I'm going to go with the lambda 1 SE. And then we are going to be putting the name of the trained model here that we just created. And then let's run this predict function. ypreds. Let's display the values of ypreds right here. And you see that these are my predictions for my training data. Okay. Let's put it in contingency table format, and let's run our summary of our confusion metrics. So this is my confusion metrics. It's similar to the one that I obtained by using logistics regression. But let's calculate the accuracy, sensitivity, and specificity. Remember, these are the libraries that we have to load first and then call confusion metrics with the name of this contingency table. All right, so let's take a look at the accuracy number. Well, accuracy number is not really as good as logistics regression. It was like 85% now with this trained data. I do have 82% sensitivity and specificity. I don't remember these values, but make sure that you check those with the ones that we obtained on the logistic regression. This would be my training accuracy, training sensitivity, and specificity. All right, let's see if we can make the predictions on the test data. Well, nothing is going to change. I will be still using the trained model that I have earlier. Okay, my S value is going to be the same lambda value that I'm using, right? Hopefully with these 4 independent variables. The new X is going to be this time test X. Remember, test X includes all the independent variables in my test data. And the type is class. So let's predict ypreds. All right, so let's display them. These are my predictions for the test data. Let's put those in contingency table format, and let's run it. And let's generate the confusion metrics for our test data. Okay, so it is actually 73%. It is much, much less than the one that we obtained by using logistics regression. Sensitivity and specificity went down a bit as well. Well, this might be due to the fact that I am only using 4 independent variables. So remember, in logistics regression case, I was using 6 independent variables. It might be a gain too, because by removing 2 more independent variables out of the equation, I am only losing a very small amount of accuracy. Again, there's a trade-off here. If your trade-off is if your primary objective is to use less and less independent variables and explain what's going on with your problem on the dependent variable, then lasso and regressions would be terrific for you. But if you say accuracy is more important than losing less number of independent variables, then logistic regression would give you a better results. Okay. In addition to this trade-off, Lasso and Ridge can save you dealing with multicollinearity issues. Again, multicollinearity happens when you have independent variables explaining each other. Okay, so this video showed you how to do ridge classification. We showed how we can actually train a lasso model and how we can test it, and how we can look at the confusion matrices, and how we can actually look into this graph, which tells us, which lambda value that I should go with. On the next video, I'm going to show you how to do a ridge regression.